We'll consider here the simplest approximation we can use to model a solid. And this approximation is called the uniform electron gas, or the homogeneous electron gas, or the Gilliam system. So the first step for that approximation is substituting all the ions we have, or the nuclei we have in the system, with a uniform positive background. And the charge density of this uniform positive background is the whole charge density associated to, or the whole charge associated to the nuclei. That, considering the charge and neutrality of the system, is going to be the same as the electronic charge associated to the electrons. And that is the number of the electrons times the charge associated to the electron, but in atomic units is 1. So the charge associated to the electron is going to be N, which is going to be the same as the charge associated to the ions or to the nuclei, over V, which is the crystal volume. So that's the ionic charge density we have for that uniform positive background. So next we're going to analyze which is the Hamiltonian we have when the ions are substituted with this uniform positive background. And this is the Hamiltonian we have for the system. Here we have the kinetic energy associated with the electrons. Then we have the interelectronic interaction. Just remind you that this 1/2 here is just in order to avoid double counting the electrons, interaction between the electrons. Then we have the interaction between the electrons and the ions, that as we have substituted the nuclei with a continuous positive background, the summation over the position of the nuclei has been substituted with an interval here. And this rho is, as said before, is the ionic charge density. And finally, we have the interaction between the ions, which is the potential energy associated to this positive charge background associated to the nuclei. So this is the Hamiltonian we have in the system. But in the uniform electron gas model we're going to make another step. We're going to consider that besides substituting the nuclei with this uniform positive background, we're going to consider that the electrons are also uniformly distributed in the system. So the electronic charge density, which is going to be, of course, the same as this uniform positive background we have considered before. And in this case, with this second step we have in this approximation here, the Hamiltonian we have in the system is going to be like that. So again, we have the kinetic energy associated to the electrons. Besides that, we have, this is the interelectronic interaction potential here, that as we have substituted that with a uniformly distributed charge density, this summation here is going to change to an integral over the whole space, considering that the charge density, the electronic charge density, is n. So that is going to be substituted with this one. Then again, this summation here is substituted, or this is the interaction again between the electrons and the ions, and this summation here, considering that the electrons are uniformly distributed, is going to be substituted with this integral over the position vector of the electrons times the electronic density. And considering that the charge of the ionic charge density and the electronic charge density are going to be the same, we have another n squared here. And then again, we have the same interaction potential associated to this uniform positive background associated to the nuclei. So as you can see here, these three terms here cancel each other. So all the contribution associated to the interaction potentials are cancelled. And the only term left here is the kinetic energy associated to the electrons. So considering the uniform electron gas approximation to describe this system, the only term left in the Hamiltonian is the kinetic energy of the electrons. So basically it means that the electrons move like free. So the next step, we are going to analyze what happens when we have such an approximation. What's the energy of such system, considering that within that approximation, the electrons are moving freely.